thermodynamical system, surroundings, types of systems, classification of properties, classification of processes and concept of heat. In continuation, today we are going to discuss some examples which will help in better understanding for types of processes, concept of work, pressure volume work, internal energy, thermal equilibrium and zeroth law of thermodynamics and first law of thermodynamics. Here is an example which will show different types of processes. 1 mole of an ideal gas is put through a series of changes as shown in the graph, in which A, B and C mark the 3 stages of the system. At each stage, the variables are shown in the graph. Now you have to calculate the pressure at 3 stages of the system and name the processes during the changes A to B, B to C, C to A and the overall process from A to B to C and to A. At stage A, volume is 24 liters, temperature is 300 Kelvin and number of moles are given in the problem, which is equal to 1 mole. R is 0.0821 liter atmospheres per Kelvin per mole. If we substitute all these values in the ideal gas equation, PV is equal to nRT, we will get pressure equal to 1 into 0.0821 into 300 divided by 24, which we will get 1.026 atmospheres. At stage B, volume remains the same, but temperature changes from 300 Kelvin to 600 Kelvin. Thus, according to the pressure law, the pressure will be doubled at B with respect to A. Therefore, pressure at B will be equal to 2 multiplied by 1.026 atmospheres, that is 2.052 atmospheres. At stage C, temperature is 300 Kelvin and volume is half of that of stage A. Thus, according to Boyles Law, the pressure at C will be doubled with respect to A. Hence, pressure at C will be equal to 2 multiplied by 1.026 atmospheres, which is equal to 2.052 atmospheres. Now, during the change from A to B, volume remains constant, hence the process is isochoric. During the change from B to C, the pressure remains constant, hence the process is isobaric. During the change from C to A, the temperature remains constant, hence the process is isothermal. Overall, the process is cyclic as it returns to the initial state. In thermodynamics, work is an essential property. When the change in the state of a system occurs, the energy is transferred from or to the surroundings. This energy can be transferred in the form of heat or mechanical work. In elementary thermodynamics, the only type of work which is considered is work of expansion or compression of the gas. This work is also known as pressure volume work or PV work or work of expansion. Consider a gas contained in a cylinder fitted with a frictionless piston. The pressure, that is force per unit area of the gas P, exerts a force on the piston. This can be balanced by applying an equal but opposite force from outside on the piston. Let this opposite force is designated as P external. You must remember that it is the external pressure P external and not the internal pressure of the gas which is used in evaluating work. This is true whether the work is of expansion or contraction. If the gas expands at constant pressure, the piston would move through a distance of L as shown in this figure. The cross-sectional area of the piston is A. Now, work will be equal to force into distance, as you know by the definition of work. Hence, work will be equal to F multiplied by L. Here, L is the distance through which the piston has been moved in doing the work of expansion. Since pressure is force per unit area, hence F will be equal to external pressure multiplied by area. Here A is the cross-sectional area of the piston. From equation 1 and 2, we will have W, that is work, is equal to external pressure multiplied by cross-sectional area multiplied by distance, that is L. Now, A into L is the change in volume. Hence, work will be equal to external pressure multiplied by delta V. Delta V is the increase in volume of the gas during the expansion. Since the system is doing the work on the surroundings, therefore, this work will have a negative sign. Hence, W will be equal to minus P external multiplied by delta V. During the work of compression or contraction, work will be done on the system by the surroundings. Hence, this work will have a positive sign. Therefore, W will be equal to plus P external multiplied by delta V. Work may be expressed in the units of dynes centimeter, ergs or joules. Work can also be expressed as the multiplication of the units of pressure and volume, that is in liters atmospheres. It depends on the process by which the particular state has been attained. Work does not depend on the initial and final state of the system. For example, the work in changing the volume of the gas through 1 meter cube can be 100, 10 or 1 joules depending on the pressure if it is 100, 10 or 1 Newton per meter square respectively. The work done will be equal to 0 if the gas expands in vacuum. The symbol of work is taken to be W. The sign of work is positive if the work is done by the surroundings on the system. During this process, energy of the system increases. The sign of work is taken to be negative if work is done by the system on the surroundings. The energy of the system decreases during this process. Here is an example to calculate pressure volume work. A gas expands by 0.5 liters against a constant pressure of 1 atmosphere. Calculate the work done in joules and in calories both. As you know that work is equal to minus external pressure multiplied by delta V, that is volume change. Hence, work will be equal to minus 1 into 0.5, which is equal to 0.5 liters atmosphere. Now, 1 liter atmosphere is equal to 101.32 joules. Therefore, the work of liter atmospheres can be converted to the work in joules by multiplying the work of liter atmospheres with a factor of 101.32. Therefore, this work is equal to 0.5 multiplied by 101.32 joules, that is minus 50.66 joules. The work of liter atmospheres can be converted to the work of calories by multiplying it with a factor of 24.20. Hence, 0.5 liter atmospheres will be equal to 0.5 into 24.2 calories. Therefore, the work in calories will be equal to minus 12.1 calories. For unit conversions, you must remember that 1 joule is equal to 0.2390 calories. 1 calorie is equal to 4.184 joules and 1 liter atmospheres is equal to 101.3 joules, 1.013 into 10 to the power 9 ergs and also 24.206 calories. There is another example to calculate the work of expansion. Calculate the work done in open vessel at 300 Kelvin when 92 grams sodium reacts with water. Assume ideal gas behavior. Now you must know the reaction between sodium and water. It is sodium plus water, you will get sodium hydroxide and hydrogen. Here is the balanced equation for the reaction. Number of moles of sodium will be equal to mass of sodium upon atomic mass of sodium, that is 92 upon 23, which is equal to 4. Now moles of hydrogen formed will be equal to half of the moles of sodium used, that is half multiplied by 4, which is equal to 2. Work is done in giving out 2 moles of hydrogen. Therefore, W will be minus pressure into volume of hydrogen. Here delta V will be equal to the volume of hydrogen itself, because initially the volume of the gas is 0. Now PV is equal to nRT. Therefore, we can calculate the value of nRT to get the value of PV. Number of moles of hydrogen are 2. Therefore, nRT will be equal to 2 multiplied by 8.314 multiplied by 300, which is equal to minus 4988.4 joules. The hydrogen liberated pushes the atmospheric gases back, hence does the work on surroundings. Therefore, this work will have a negative value. If this reaction was done in a closed vessel, then delta V will be equal to 0 and work done will be equal to 0. There is another example to calculate the work done when water vaporizes. Calculate the work done when 1 mole of water at 373 Kelvin vaporizes against an atmospheric pressure of 1 atmosphere. Assume ideal gas behavior. The volume occupied by liquid water will be negligible and thus volume change is equal to the volume of the water vapor only. Now applying the ideal gas equation, PV is equal to nRT, we will get the value of volume. Volume will be equal to 1 multiplied by 0.0821 multiplied by 373 divided by 1, which is equal to 31 liters. This is the volume of water vapor and this is also equal to the volume change, because the volume of liquid water is taken to be negligible. Now, W will be minus pressure, which is external pressure, multiplied by delta V, which is the volume of water vapor. Work will be equal to minus 1 multiplied by 31 liter atmospheres, which is equal to 31 multiplied by 101.3 joules, means minus 3140.3 joules. A fundamental parameter in thermodynamics is internal energy. This internal energy is denoted by the symbol U or E. The internal energy of the system is the sum total of all types of energies of the system. Internal energy contains all kinetic energy and potential energy. As internal energy includes all kinds of nuclear energy, mass equivalence and molecular energies, it is not practical to measure the absolute value of internal energy. The changes in the value of internal energy and its relationships with other parameters is only used in thermodynamics. The internal energy of a system is determined by the state of the system and not by the path by which that internal energy has been attained, or not on the process by which that internal energy has been stored. Hence, the internal energy is a state function. For example, if we consider the heating of 1 mole of liquid water from 0 degree Celsius to 373 Kelvin, that is 100 degree Celsius, the energy change is 1.8 kilocalories. This energy will remain same regardless by the method by which that energy has been transferred to 1 mole of water, that is by heating, by doing mechanical work, by electrical means, or by any other process. As the value of internal energy depends on the mass contained in the system, hence internal energy is an extensive property. The symbol used to represent internal energy is capital U or capital E. It is neither possible nor required to measure the absolute value of internal energy. If the change between two states is taken as equal to delta U or delta E, then delta E will be equal to final internal energy minus initial internal energy. The change in internal energy will have positive sign if final internal energy is greater than initial internal energy, and delta E or delta U will have negative sign if final internal energy is less than the initial internal energy. The energy can be transferred to or from the system in the form of heat or work. The SI units of internal energy are joules. There is another unit for internal energy which is not the SI unit, it is calorie. We can say that internal energy has some characteristic properties. Internal energy of a system is an extensive property. Internal energy is a state property. The change in the internal energy does not depend on the path by which the final stage is reached. There is no change in internal energy in a cyclic process. Now we are going to discuss the concept of temperature, thermal equilibrium and Zeroth law. When a hot body is kept in contact with a cold body, the heat transfers from the hot body to the cold body. The hot body becomes colder and the cold body becomes hot. The transfer of heat from the hot body to the cold body is a non-mechanical process. The energy which is transferred from the hot body to the cold body non-mechanically is called heat. The two bodies are said to be in thermal equilibrium if no heat transfers from a body to the other. The temperature concept can be defined here. If the two bodies are in thermal equilibrium and no heat transfers from a body to the other, then it is said that the two bodies have the same temperature. Depending on the concept of thermal equilibrium, Zeroth law can be defined. It states that if two systems are in thermal equilibrium with a third system, then these two systems are also in thermal equilibrium with each other. Conversely, this law can also be stated as if three systems are in thermal equilibrium together, then any two systems taken separately are also in thermal equilibrium with each other. Now, let us consider the three systems A, B and C. If A is in thermal equilibrium with C and B is also in thermal equilibrium with C, then according to Zeroth law of thermodynamics, A and B will be in thermal equilibrium with each other. An important law of thermodynamics is the first law of thermodynamics given by Robert Meyer and Helmholtz. The first law of thermodynamics states that the total energy of an isolated thermodynamic system is constant. The law is often referred to as the conservation of energy and implies the popular interpretation of the first law, namely that energy cannot be created or destroyed. The change in internal energy can be done in two ways, either by transfer of heat from surroundings to the system or from system to the surroundings, or by doing work on the system or by doing work on the surroundings. Consider a system whose internal energy is E1. If the Q amount of heat is absorbed by the system, then final internal energy will be equal to E1 plus Q. But if W amount of work is also done on the system, then final internal energy will be equal to E1 plus Q plus W. Therefore, E2 will be equal to E1 plus Q plus W, or we can say that E2 minus E1 equal to Q plus W. This E2 minus E1 is the difference between the final internal energy and initial internal energy, that is, it is equal to delta E. Therefore, we get delta E is equal to Q plus W. This is the mathematical statement of first law of thermodynamics. In this statement, Q is heat absorbed by the system and W is work done on the system. But if work is done by the system on the surroundings, the statement for first law of thermodynamics becomes delta E equal to Q minus W, because work takes negative sign here. For first law of thermodynamics, it can be said that the net energy change of a system is equal to heat absorbed by the system plus work done on the system, or heat absorbed by the system minus work done by the system on the surroundings. Work and heat are path functions or non-state functions, because work done by the system or on the system and heat lost by the system or by the surroundings does not depend on the initial and final state of the system, but these two properties depend on the path or process by which that state has been reached. First law of thermodynamics can also be defined in many other ways, first of which is whenever energy of a particular type disappears, equivalent amount of another type must be produced. The second definition is the total energy of a system and surroundings remain constant or conserved. And the third definition is it is impossible to construct a perpetual motion machine that can produce work without spending energy on it. So, today we have discussed the concept of thermodynamical work, that is pressure volume work, internal energy, thermal equilibrium, Zeroth law and first law of thermodynamics. In continuation, in our next lecture, we will continue with some examples related to